This video is on enzymes and enzyme inhibitors. Enzymes are absolutely essential for life because without enzymes, biochemical processes are too slow. So you need them in order to keep up with your processes. These enzymes speed up reactions by as much as 10 to the 16th times. So if you just think 10 to the 6th is a million, so 10 to the 16th is a very large number. Quadrillion, I think that would be. Only one chiral product will be produced as a result with your enzymes. And your enzymes do not change during the reaction. That after the process is complete, they will just look for another, what's called a substrate, to do the same thing again. So one enzyme is good for many different substrates. Your enzyme names generally end in ASE. So for example, the enzyme lactase, ending in ASE, what this does is this catalyzes the hydrolysis of lactose into glucose and galactose. So if you're lactose intolerant, your lactase enzyme is not functioning properly, or you just don't have it at all. So something called the enzyme substrate complex. So this, the way you have to think of this is kind of like a puzzle, that each piece needs to be, one piece needs to be chiseled out perfectly to fit the other puzzle piece's shape. And there's something called an induced fit model of enzyme catalysis. Your substrate or your reactant is binding or connecting to a pocket or groove within the active site on the enzyme. So this 3D shape of the active site accommodates the shape of the substrate. And the next slide here will show you what I mean. The enzyme then undergoes conformational change upon bonding to the substrate, which is called an induced fit. And then after the reaction, the product is released, and then the enzyme begins the entire process again. That it doesn't just go away, it's not changed at all, it's ready to do the same thing. So here you have your enzyme labeled E, and notice there's a certain shape to it. So it is going to look for a substrate, S, that perfectly fits in there. So this S is a perfect match. So it comes together at this active site. And then that does its magic. It lowers activation energy, it increases the reaction rate, and then when it's finished, your product will leave, and look, your enzyme did not change at all from the beginning. So it's like a puzzle piece. And again, this is called your induced fit model. Lowers activation energy, increases reaction rate. So your pH and temperature dependence of enzymes. So we can split this up. So your native conformation required for optimal function depends on pH. Most of the enzymes out there have optimal pH values at about 7.4, your physiological pH, 7.35 to 7.45. However, others do have different pHs, depending on where the enzyme is used in the body. So, for example, we have our salivary amylase here, and this is right at your 7 value. But your pepsin here, this is a gastric enzyme. So in the stomach, That's better at a lower pH because we know our stomach is acidic. So this enzyme is optimal at around a 2 pH. So that can change, but a lot of your enzymes do have pH values around that 7 range. It also depends on temperature. So on the right side over here, an optimal temperature value around 37 degrees Celsius. This is degrees Celsius here. If the temperature is too low, that will slow down the reaction rate. And then if it's too high, we know that can denature the enzyme. So it has to be that just right temperature here, around 37. So this question says, to achieve its maximum catalytic power, what pH is optimal for a reaction catalyzed by pepsin, an enzyme found in the stomach? And so use the graph. So not a hard graph to read. We're just looking for pepsin, and the optimum pH is right down the center. So our answer there would just be a 2. Okay, enzyme inhibitors. So these are compounds that bind to an enzyme and prevent it from working. So these are trying to ruin the enzyme's function. These may be poisons, for example. They may be specific inhibitors, which are pharmaceuticals that target a single enzyme, binding reversibly to the enzyme for a specific reason. Or these might be antibiotics that bind irreversibly to bacterial enzymes. So we can do it on purpose and we can make it reversible, or we can do it on purpose and make it irreversible, or we just don't do it on purpose at all and it's some type of poison. There's 2 types of these enzyme inhibitors. So we have something called a competitive inhibitor, and we have something called a non-competitive inhibitor. And we'll get to these in the next couple of slides. The biggest difference is your competitive inhibitor is competing with your substrate. So both of them want to get to the active site, and it's a competition. Your non-competitive inhibitor does not want to go to the active site. It can bind anywhere on the enzyme and still do damage. So competitive, again, it competes with the substrate. It looks similar to it. It has the same puzzle piece that it needs to have, and it blocks the substrate from binding. It gets there first. Now, the effectiveness depends on the concentration of both the inhibitor and the substrate. Whoever has the higher concentration wins. So whoever has higher concentration wins. So if the inhibitor's concentration is higher, that's going to go in the enzyme. If the substrate has a higher concentration, that's going to go in the enzyme at the active site. Pharmaceutically talking, for that to work, the inhibitor concentration must be maintained. So that is why, interestingly enough, that's why medicine is usually given at regular intervals, twice a day, 3 times a day, 4 times a day, just because that inhibitor has to stay constant. So it's very important to give medicine as prescribed. And your non-competitive inhibitors, again, that's not competing for the active site. That's binding somewhere else on the enzyme. But even when this binds somewhere else, the enzyme changes. It undergoes conformational change. When it does that, the active site changes, and then the substrate cannot bind, right? That puzzle piece will not fit in the other puzzle piece. Here, with non-competitive inhibitors, the concentration of the substrate does not matter. So with competitive, it mattered, right? Whoever had the higher concentration wins. Here, the substrate concentration doesn't matter. The enzyme only works when the inhibitor concentration decreases. So that is a big difference between the two. So here is an example of non-competitive feedback in cholesterol synthesis. So this is pretty interesting because cholesterol inhibits its own synthesis when the concentration is high. So we have this HMG CoA, and this converts to mevalonate. And this is just one step here, and this is a multi-step pathway, but this is the first step right here. This is your enzyme, right? ASE, it ends in. So what happens once it goes here, your cholesterol, this non-competitive inhibitor, will go to the enzyme and it will inhibit it. And the enzyme activity is only restored when the cholesterol concentration drops. So it's kind of a tricky game, because if cholesterol is too high, that's bad. But low cholesterol is actually too bad too, which a lot of people don't know. It has to kind of be at that sweet spot. So your cholesterol, when it's high, this will come in and get the enzyme. And then again, the enzyme won't be good until the cholesterol is lowered. So it's a little bit of Le Chatelier's principle going on here with what we need to happen. So 2 questions here, just going over these two. Where on the enzyme do the following types of inhibitors bind? So you have your competitive inhibitor, and that's competing again. So that is going to bind on the active site in that puzzle piece. And your non-competitive, that will be any other site, just not the active site.